Welcome to Lecture 2 for Math 5027. So we're picking up where Lecture 1 left off. We were talking about metric spaces and proving that functions that we often call D, that's like a distance function, are metrics on certain spaces. And so in this example, we're really just focusing on examples of metric spaces and some properties of a metric in this set of lecture notes. The first example picks up with little l infinity. Now this example was chosen because it could start to challenge how comfortable you are with notation. And you're still going to see, I have this proof, and it follows the same exact 4 steps that you always have to go through to prove that a function is a metric, right? You have to prove that the function maps to numbers that are greater than or equal to 0, but they're numbers. They're never infinity, right? So, it maps to between 0 and infinity. You have to prove that it's symmetric, that d of xy is, that you have to prove that if d of xy is equal to 0, then that only happens if and only if x is equal to y. And then you have to prove symmetry. That was what I was just trying to say there. D of xy is equal to dyx. And then, of course, the triangle inequality, which is usually where a lot of the work is. Those are those 4 steps. So this is already written out for you. The purpose isn't to read through all the details. You can read through those here. I ask a question that we can talk about in class. Why is this function d defined as a sup instead of a max? But also, I think it might help for me in this lecture to say a little bit about the space L infinity, because you might not have seen a space like this before. In undergrad analysis, you probably focused a lot on R. You're probably very used to proving things involving the real numbers. Now, you've probably seen sequences of real numbers, and I'm talking about real valued bounded sequences for L infinity. So you have some experience with bounded sequences in the reals if you've taken a typical undergraduate elementary analysis class. In such a class, you usually prove something that, hey, if I have a sequence of real numbers that converges, that's bounded. So that's often shown something like this, like, hey, if I have S sub n is a subset of the reals, right? So some sequence of the reals in the sequence notation, and you have that S sub n converges to S, then a theorem says, hey, convergence implies bounded, all right? So that's something you might be familiar with. But this is a space where every single point is itself a sequence. And it's not just a real valued sequence, it's a bounded sequence. So certainly it contains convergent sequences as individual points. A single point is an entire sequence. So it could certainly contain convergent sequences because convergent sequences are bounded. Convergent sequences of real numbers, as I'm talking about here. But there's bounded sequences that aren't convergent. For instance, there's the sequence, you could say C sub j, that's given by 1, negative 1, 1, negative 1, 1, negative 1, and so on, right? This alternating sequence of 1s and negative 1s. So that's usually one of the first examples of a real valued sequence that you encounter where you use the logical negation of convergence to show that that's not a convergent sequence at all. So something that you might be familiar with. So such a sequence like that is also an individual point in here. Now, taking all that in, the idea that a whole sequence of real numbers could be a point in a space, a single point in the space, is actually not that strange. It just might be unfamiliar. You certainly are familiar with the real numbers, but you're probably at least familiar with the Cartesian plane, which we call R2, in which case we would use the notation that I'm using for this here. I'd say like I'm using this Greek letters. Let me rewrite this a little nicer on the screen. Just take a second to move my surface around. So I could think of a point x as some vector c1 and c2 is the Greek letter c that I'm using for the numbers, that is something that's a point in R2. And I could think of x, maybe instead of being in R2, I could think of like c1, c2, c3 as something that's in R3. And I could think of a point, a single point, being a 10-dimensional vector or 100-dimensional vector. And you probably have no problem at least conceptualizing that finite vector for any finite dimensional space. This is somehow a subset of, maybe we could use this notation. Little l infinity is contained in R infinity, where R infinity is just an infinite dimensional vector of real numbers, which you could represent, you could think of it like a sequence. So if you conceptualize it that way, it maybe starts to seem a little bit more straightforward. hopefully a little bit less strange. And then you can conceptualize each point more clearly. Now you might ask yourself, why are we not just using x sub 1, x sub 2, and so on? Like, why is Troy not saying x is just x sub j as something that's in L infinity? So that I think of this, x as something where it's x1, x2, x3, and so on. Well, there's a good reason for that. We'll eventually start talking about, actually, I believe next week, sequences of points in a space. So then you're going to talk about sequences of points, for instance, in L infinity. We'll work with that. Those will be some of our examples of these little LP spaces, and in this case, little L infinity. And then you need to use notation like, well, I'm talking about x sub n as a sequence in L infinity, and now you have to have some notation that makes sense, because if you're using x sub n to denote the individual points in L infinity, you can't really use this notation very cleanly. It starts to get very messy. Whereas you could talk about, with some double notation, you could say, well, there's maybe c sub j coming from for the nth sequence, or excuse me, the nth point in the space. So anyway, that's just a little foreshadowing of where things go, but that's just to get you used, or get you in the right frame of mind to just think about what this space even is for that example. So that's really what I want to spend this lecture talking about, or in terms of page 1. I don't want to talk about all the details here, other than to say your proof should definitely start with just taking 3 points. I took x, y, and z. I'm denoting the individual terms and the sequence of real numbers associated with each of these points in the space L infinity as c sub j's, eta sub j's, and gamma sub j's. And then I'm talking about the individual positive, non-negative, I should say, non-negative real numbers that bound all of the terms in each of those sequences separately. Although technically I don't really use the c sub z in the proof. All right, but I want to move on to this next result. This is the little LP space. I mentioned little LP in talking about that previous example. These are also sequences. An individual point is something that's sequence, but it has some sort of summability requirement. Now, in order for this to be the case, these sequences, right, each point being a sequence, that sequence that I just circled actually has to have the property that it converges to 0. You might remember that from calculus, that if you can sum up, if you have a series and it's summable, meaning it's, less than infinity when you add it all up, that implies that these terms have to converge to 0. And the idea of them being an LP means that when you raise them to the p power, it's summable, which is describing some sort of rate of convergence to 0 that these individual sequences have to have. These are actually really important spaces in practice, and we can talk about more in class why they are important. You can look them up too. You can Google and see, where do little LP spaces come in? What about big LP, capital LP spaces? These are all important types of spaces and examples of metric spaces that you'll come across. Look up the Minkowski's inequality. It's kind of like the Cauchy-Schwarz inequality. See if you can prove that this is a metric. If nothing else, outline the 4 steps. Start, take like, hey, x, y, and z are points in the space, and see if you can start filling in the details to show why this is in fact a metric. That's a good exercise for you. Another good exercise for you is to work with product metrics. Like if I take just 2 metric spaces x and y, and I define a metric space M as the product of them, show that all of these things are metrics. So d sub x and d sub y in this case are the metrics for x and y respectively. And then if you combine them in certain ways, in this case, this looks like kind of the Cartesian Euclidean product metric. This is this max. That looks very similar to something that we were just doing here using a sup. But why is this a sup and not a max? It's a good question for you to consider. But you look at this and say, you know what, that just the absolute value of the difference between 2 numbers is? That's the metric on R. That's the usual metric that you have on R. So you could, right, I said L infinity. You might think of L infinity as contained in R infinity, and you might think of that as R times R times R, an infinite number of times. And this is very much like a generalization of this metric for when you have an infinite number. But when you have an infinite number, this can't be max. It has to be sup. Try to figure out why. If you don't know why, think about it. Anyways, good exercise for you. I'll let you try to do this one. It's pretty straightforward. And you can do this you could do this very simply for yourself. If you're having trouble with the abstraction, take x and y to be equal to r with the usual metric. My handwriting here is terrible, I'm sorry. But take them to both be the real, and then take m to be r squared. And then you're literally talking about your typical Euclidean metric that you're familiar with. This is something that would be related to what we call like an infinity norm metric. And then this is the taxi cab metric. So look at it, try to figure it out, think about it. All right, now a metric space with metric D can always be remetrized so that the metric becomes bounded. So simply define the bounded metric in this way. So there's this example here. And you're supposed to prove this is a metric. So the idea here is D is already a metric. If you define rho, that's the Greek letter rho, in the following way, you're actually defining a new metric on M, and it's a bounded metric, right? One of the properties we have, remember property 1, is that the metric should map between 0 to infinity. This metric actually the metric can map to arbitrarily large numbers, just not infinity. So it's an unbounded function, possibly, but rho maps everything between 0 and 1. All right, so that's something to hopefully you can figure out by seeing the form of it. And I have a note for myself here, because you don't have this in your set of notes, is to put this in the video. So how do you prove this, right? Well, properties 1, 2, and 3 follow from D being a metric. Students should fill in the details. You should try to fill in the details for that. And as usual, the triangle inequality is a sticky point. If you try to prove the triangle inequality for this, it gets a little hairy. So I just provide some scratch work in an idea about how you would go about proving it. How would you figure this out? How do you solve the problem? Well, imagine you pick 3 points. This is some scratch work. That's what I always mean by SW when I write SW. If I picked 3 points, P, Q, and R, in M, I'm using the notation for this problem here, then you need to show that rho of PQ is less than or equal to rho of PR plus rho of RQ, right? The distance between P and Q's got to be less than or equal to the distance from P to R plus the distance from R to Q. That's your triangle inequality. Well, if you write out what that is in terms of R, it means you got to show this. So if you look at that, like if I'm a student, the first thing that I got to do is I got to simplify my life. I'm going to simplify my notation. Take A, B, and C to be the non-negative real numbers defined by the distances dpq, the distance between P and Q, the distance between P and R, and the distance between R and Q using the metric D. Now, since D is a metric, start taking stock of what you know. This is just how I would go about trying to solve this if I was a student. I would know, well, look, D is a metric, so A is less than or equal to B plus C. Okay. How can we use that to get that, if we substitute this notation in, A over 1 plus A is less than or equal to B over 1 plus B plus C over 1 plus C. So it's not exactly clear. Why should that follow from this? Because we've changed these quantities, right? B and C certainly may be larger than A, but then 1 plus B and 1 plus C are larger than A, and we just divided B and C then by bigger numbers, which could make them even smaller than the way we divided A. So it's not clear why this should be true necessarily, or at least it's not clear to me. So what's a good solution strategy? If you're looking at something kind of saying, this is what I need to get, but I don't know how I'm supposed to get there. Start with what you need. Remember, like when you're a student and you're looking at an answer in the back of the book and you try to work backwards from that answer and reverse engineer the solution? It's kind of what you do here. Say, wow, I need this to be true. So let me start manipulating things, do some symbolic manipulation. I sometimes call this symbolic gymnastics, and just put together a bunch of things that if that were true, other things would be true in kind of a set of if and only if statements. So the first thing I do, and I'm not going to go through all the details here. You can pause this and hopefully write down all the details for yourself. But I wouldn't necessarily do that right away. The point is, I first do a common denominator, right? If I've got a bunch of fractions, what do you do when you have a bunch of fractions? You need to combine things. Work out a common denominator. But I just went ahead and multiplied by 1 plus A times 1 plus B times 1 plus C to both sides of the equation. So I get rid of all the denominators, make my life easy. And so that's how I get to there. I multiplied both sides of that inequality by 1 plus A times 1 plus B times 1 plus C. and then I'm canceling out the certain terms in the denominator. Then I just expand. I collect the like terms on both sides of the inequality, which get canceled out, and then I'm ultimately I'm left with this, and I'm like, wow, is that true? Through my collection of terms and cancellation. Well, yes, it is, because A is less than or equal to B plus C. And if A is less than or equal to B plus C, and A, B, and C are all greater than or equal to 0, then if I add something that's greater than or equal to 0 to this other side, I can only make it larger. So yeah, this is true. This follows from the fact that A is less than or equal to B plus C, and A, B, and C are all non-negative numbers, which means that 2BC plus ABC is something that's greater than or equal to 0. So that inequality follows. So my suggestion to you is, before you even prove this metric, make this lemma right here. That if A, B, and C are greater than or equal to 0, oops, that's not quite the lemma I want. Let me fix it here. And so you're going to see I make errors sometimes, but hopefully I correct them. And A is less than or equal to B plus C, then A over 1 plus A is less than or equal to B over 1 plus B plus C over 1 plus C. Prove that lemma by basically working this backwards, heading in that direction I just drew with that arrow. Prove that lemma first, and then hopefully you see that you can then use that lemma to prove the triangle inequality by just making this notational substitution and saying, hey, follows from the lemma. Like I said, triangle inequality is where all the work is, and sometimes you might want to offload that work to a lemma. And you might figure out that lemma by doing some scratch work. So that's what I want to say about this page of the lecture notes. And I want to start cutting this short, so I'll just go to the last page, which I don't have much. I just want to say a useful inequality is the reverse triangle inequality. It says that the absolute value of the distance between x and y and the distance between y and z, the difference between those, the absolute value of those, is less than or equal to the distance between x and z for all x, y, z that are in a metric space M. I'm using the notation of the book, even though I like using x's for metric spaces. I'm telling you to prove it. You should prove it. I give you a hint, and I basically work out the details that you need, and if you follow this hint and think about it, you should be able to see how to go the other way. I prove that d of xy minus d of yz is less than or equal to d of xz. You need to prove that d of yz minus d of xy is less than or equal to d of xz. Because if you basically show that a minus c is less than, more sensible choice here. If a minus b is less than or equal to c, and b minus a is less than or equal to c, then that's how you prove that a minus b is less than or equal to c. If you show these, that means this. That means the absolute value is less than that. So I basically show you one direction, so hopefully it should be straightforward for you to show the other direction. But if you have trouble with it, it's fine. I can help you out. Just try to think about it and try it for yourself, and that's something for you to fill in. So that's it for this lecture. Thanks for listening, and I'll see you in lecture 3.